Hi, my name is Yash. My team and I chose problem number 27, which deals with spring versus friction. Our problem reads, suppose you have a 0.52 kilogram object on a horizontal surface connected to a spring that has a force constant of 100 newtons per meter. There is a simple friction between the object and surface with a static coefficient of ms equals 0.107. Part 27a reads, how far can the spring be stretched without moving the mass?
Go.
Here, for 27a, this is a picture symbolizing the problem. And then right here, along the y-axis for the vertical forces, we can see that there's force normal that's being imposed onto the object. And then the weight, which equals mass times gravity, pulling it down. And we're told that the object is constant and it's not moving. So we know that these two forces cancel each other out. So we know that our F net equals our force normal minus our weight, or our force normal equals weight. And because we know that there's a static equilibrium along the y-axis with our vertical components of force.
Go.
Now we're going to look at the horizontal forces. And as you can see that we have our maximum spring force, which is 100 newtons per meters. As well, we have a static fraction, which is 0.107. And this is a unitless metric. And since since our object's not supposed to move, that means it has static equilibrium, which means the forces will, horizontal net force will equal 0. That means that the maximum force equal with the spring force will equal each other.
Now, as we talked about earlier, the normal force is going to be equal to the weight, which is mass times gravity, because like we said, we have a static equilibrium in the vertical direction. So if we plug in our values, we have 0.52 kilograms as our mass times 9.8 meters per second squared, force of gravity, equals to 5.10 kilogram meters per second squared. Right now, if we look at our static equilibrium in the horizontal direction, we know our max frictional force equals to our static friction times the normal force, which equals to our static friction, or in this case it becomes kinetic friction, times mass times gravity equals to kinetic friction times 5.10 kilogram meters per second squared. Now we have the equation that our spring constant force Fx equals to Kx. So we plug that in, we have it equals to 100 newtons per meter times x. Now in this case, x is the distance that the spring can stretch without moving, so it's the value we're looking for. So if we look right here, we have our spring constant force equals to the maximum frictional force, okay? And we use some basic algebra. We can do x equals to our kinetic friction times our F normal, or mass times gravity, divided by our spring constant force equals to 0.107 times 5.10 kilogram meters per second squared divided by 100 newtons per meter, and all of that becomes 0.0054 meters. So that is the distance that the spring can stretch without moving the object.
Go.
For 27b, the question asks that if the object is set into oscillation with an amplitude twice the distance from 27a, and the kinetic coefficient of friction is 0.056, what total distance does it travel before stopping?
So essentially, the first thing we have to do is multiply our answer from 27a by 2 to get the new amplitude, which is twice the distance from 27a. So basically, we're going to make x2 our new amplitude equals to 2 times 0.0054 meters, which was our answer from 27a. That gives us 0.0108 meters as our new amplitude. All right, now we know that the new kinetic coefficient of friction is 0.056. We have that right here. So once again, so we have that. Now we're going to let the energy at the beginning of the oscillations be seen by this. 0.5 kx2 squared equals to 0.5 times 100 newtons per meter times 0.0108 meters squared. And that gives us 0.005832 joules. Now, we're also going to look at the energy at the end of the oscillations. For that, we have our normal force times our kinetic coefficient of friction times D equals to 0.005832 joules. And we have, of course, have the equilibrium, so that's why this number and this number are equal. End, beginning, equal. So we have that. Now, in this case, of course, D is the total distance that the object travels before stopping. That's the information that we're looking for in this problem. Go.
So this represents the energy, and you can find this by doing the normal force times the coefficient of friction times the distance. It will give you 0.005832 joules. And we can be able to find the distance that the object travels before stopping, given the conditions, and we can use basic algebra to rearrange this equation to find the distance. So essentially, distance equals joules over the normal force times the coefficient of friction. And we just plug and chug with these numbers, and it will equal 0.02 meters